Good evening. So let's start today's class, and this class will be the last class of this series. So this series is named as equilibrium concepts in game theory. Particularly, the this class will be mostly about evolutionary game theory. Evolutionary game theory and the solution concept associated with it. However, let me first recall whatever we learned in these courses in this course. So we will point out what is the main thing that we have covered in this course, then we will go to the evolutionary game theory. This is the first we have learned one thing, that it is we by mathematical we can write a mathematical model to represent any strategic decision making. So specifically, we first in the first two classes we have seen that seen or we are after the question, can we mathematically represent the preferences of an agent. So first we have covered these things, that whether or not the preferences, and the preferences means the decision making of an agent, it could be human being or it could be anything. If it has preferences, can we mathematically represented? We have seen that particularly two cases. One is decision making under certainty, and decision making under uncertainty. So we have seen that this uncertainty means nothing but a situation which can be uncertain situation which can be represented by the probability, and we have seen that yes, we can mathematically represent this decision making by terms of utility. That means a real number. Now, how a one individual's decision making under uncertainty. So the decision type under uncertainty could be different for uh, can be many different rules by which one can choose decisions under uncertainty, and based on that we have find that two mathematical different utility concept can be represented. One is there will be many different concept of utility can be represented in case of decision making under uncertainty, but particularly in this course we have seen two. One is called the VNM, expected utility, and another is procedural or stochastic utility. stochastic utility. In general literature, the rational individual means this whose decision making follows the axioms of VNM expected utility theory. That agent is called the rational individual, or it is, that means, by rational in normal literature means VNM rational individuals who follows the axioms of VNM expected utility. And the stochastic utility is a case of bounded rationality, and this stochastic utility is obviously does not a agent whose utility can be represented by a stochastic utility does not follow the rules axioms of VNM expected utility theory. So thus it is called the bounded rationality, and particularly we have covered in this class which is called procedural rationality. Rational. Now we have seen the equilibrium concept associated with these two field. Equilibrium concept associated with VNM utility, or if the player's decision making follows axioms of VNM expected utility, then we know the solution concept for a strategic interaction. Solution concept for strategic interaction is Nash equilibrium. And when we are talking about the decision making and strategic interaction, one can notice that the one individual in his or her lifetime can take many decisions, and it means if those players are VNM rational individuals, then they could they in multiple strategic situations they could adapt multiple Nash equilibrium, and they can change their strategy whatever they whenever they want, and their strategy is the deliberate process of maximizing the expected utility. Why means it is not quite true, but we can, as we have discussed previously, that one individual's it is debatable whether or not that one individual's internal satisfaction or anything can be represent their utility. But we are starting in the in this particular game theory, we have started with the preference of the individual. So from the preference relation we have write the utility, and one individual always wants to maximize his or her utility, means that the individual wants the most preferred option. So that's it, that's all. However, the main point is in a lifetime, in this case, the decision maker in in their lifetime takes many decisions, many strategies. Reasons, and these are the deliberate process of process of opting for most preferred item. So that is for the solution concept of strategic interaction in Nash equilibrium. And let me again restate that what is this strategic interaction means. The strategic interaction means when multiple individuals involved in multiple involved in a so multiple individual in a certain thing or in something. So in a something or some work, in a work, so suppose multiple individuals are doing a work, then if the outcomes if the outcomes is intertwined or a outcome is depend outcomes depends outcomes depend on the strategy of every individual. So if it is true, then that work and that work is called they are strategically interacting with each other, such that because their outcome is if they know the fact that the outcome is strategically interact know that their outcomes actually depend on everyone strategy, then they will think and they will strategically interact. And in the why we are talking about these things, it will be clearer in the when we will introduce the evolutionary game theory, where the strategic interaction is present but it is little bit different from these processes. So solution concept of the strategic interaction in the case when the individuals are whenever rational, then they do then the solution concept is Nash equilibrium. Now if also then we have learned that if the agents are procedural rational procedurally rational, then solution concept is no longer Nash equilibrium. It is, we have seen that it is sampling equilibrium. Sampling equilibrium. And the above stated thing also true for this case also, because they can take many strategies in their lifetime, and they can change their strategy whenever they want. And also their strategy is a deliberate process of decision making, that they want to deliberately they want one individual deliberately wants to a option which is the most preferred according to him or her. Now our question is, means it is not true, but for the sake of generality, say that these things are the for individuals who are uh, who are capable of thinking. But if I go beyond human, so there is a debatable question whether animals can think strategically likewise like as humans do. It is debatable. So animals and we means in their every situation we don't know they are um, thinking thinking strategically or not. However, you will often find the strategic interaction is everywhere in the animal kingdom. Now the question is, if we just relax the whole set of axioms of decision making, so they are their preference. So now we are talking about, we are talking about if we are talking about, so no decision making, so decision making obviously happening there, but no deliberate decision making happening. And whatever strategy we are seeing, that strategy is determined from the birth. So that individual cannot change his strategy because his strategy is determined by birth. So suppose here, for an example, that uh, a color of a, so suppose that the color of the feather of a bird, or the aggressiveness of a lion, or it could be they can, and then the color of a lion. So these are the example where that the agents cannot change their strategy during their lifetime. Only by mutation it could the strategy of an individual change. So I am talking about in terms of, I want to talk that the strategic decision making of those individuals where the strategy is not chosen by themselves by a from a deliberate process of decision making by thinking, and it is the strategy is determined by means from his or her birth, and it is inherited from the parents, where from where it is coming, inherited from inherited parents. Can we write the solution concept for strategic decision making? So one can say that let means one can say that what is the strategic decision making then there. So since there uh, cannot take strategy, so does it true that there is strategic interaction? Now if you think for a moment and think about this formulation of strategic interaction. So strategic interaction means if if the outcomes depends on everyone's strategy, it doesn't matter the strategy is a deliberate process of thinking, or it is adapted by adapted it is adapted from parents, means it is inherited from parents, and it is means for an individual, his strategy is determined by its birth. It is the strategic means the if as long as the strategic interaction depend on the strategies of everyone, it is called strategic interaction. It doesn't matter from where the strategy comes. So we in general we can say that yes, for this case also we may see the strategic interaction. Now let me give you an example, and this example is this example is the example from where the evolutionary game theory comes. And as the name suggests, the evolutionary game theory, you means there is a hint that this part of game theory contain evolution itself. Means this means evolution is in the formulation of this game theory. So it is first tossed by these this concept is first tossed by these John Maynard Smith. So there in that time there was a debatable question which is obviously strategic interaction. What is the debatable question is that in nature we often observe that two animals two animals often fight with each other for getting a mate. So their conflict means there some conflict arises during mate choice. However, you will find that during this during this mating choice, some kind of rituals are there. Instead of going to a serious fight, they evolve to show some kind of ritual. So suppose for case of a stag, so when you will see that these stags or deer, male deers who have a big horn, now when they came to a ground to for mating, they will show that who is the who is the fitter for reproduction, who has the means most genetically fit. And if one male can show that he is genetically more fitter than the other individuals, then he will be successful in mating. And so in this case you will see that a serious kind of fight can escalate, and due to this serious kind, if they 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 fight seriously with each other, then obviously with this big dangerous horn they may inflict serious injuries to each other. And due to these injuries, one of the individual might become seriously one might have serious injury, and due to this serious injury the the fitness of one individual can decay. But however, you will see that these fights seldom escalates into such serious injuries. So so I am talking about why it is happening that some kind of rituals showing evolved to determine who is fitter and going to get a mate. Now this may be means rather than this, they may they may uh, they may seriously fight with each other and may inflict some serious injury, and they do not do these things. Now obviously there are, if you see, if you go for the example of this deer, you will find that some individuals are very aggressive, they always want to escalate the fights. However, there will be some individuals who will be some dormant, they don't want to fight that much, they don't want to show that such aggressiveness. Now why is that so? Why evolution selects such in such way that many of these mating choice or many of these other fight does not escalate into a serious fighting where each of them inflict each other a serious kind of injury. So this was the question. Now in the initial phase, it was thought it was thought that it may be beneficial, it may be beneficial for the species. So now we are going to the layer of evolution. Now in the previous example we have, in a sense, we have not in a sense we have see a example, a classical example of strategic interaction in case of animal during their mate choice. And as you can, from if we can recall from our past lectures where we introduced the normal form games, where we have seen such kind of game. So in case of, it is like two neighbor countries fighting with each other for having a nuclear bomb. So one may be showing aggressiveness and one may be become dormative. So it is kind of a hogged up kind of game situations. So you can see this situation is a naturally modeled by the situation hooked up game. So so that is, this situation is actually saying a strategic interaction situation. Now it has been thought that it had been said by these early developer of evolutionary game theory. So there was the puzzle is that it has been thought that this is the both this aggressive strategy and dormant strategy present there in a species, because it is beneficial for the species. If both become very aggressive, then they might inflict serious injury and some of the individual will die. So that's why it is not beneficial for the species. That is why maybe it is there. And Maynard asks the question that since the evolution works on the individual level, it cannot be true, means you cannot say that it is beneficial for the species. That is why you are seeing the existence of these two strategies. If you assume that the evolution evolution works on individual level, not in works not on group level, so by individual level means I am saying into gene level. So why, I mean, how one can explain, if it is true that evolution works on individual level, that means in gene level, then how one can explain that it is beneficial for the species. That is why these kind of strategies are there in the in general in animals world. And you see, so since there is a problem with, in the early days there is a, now it is much clear that animals are capable of making decision like us. So in those days it is very debatable that whether animals can also do thinking like us. So that's why it was being thought it that animals are, uh, in some senses, in some cases the strategies are, suppose that the size of their horn is cannot, that one individual cannot determine the size of the horn. Uh, it is the size of a horn is, if I treat the size of a horn as a strategy, then you have to agree that the size of a horn is determined from the birth. So this, if I use, if I think this is a strategy, then we have to think about that this strategy is get is inherited from his parents by the genetic material. So in this way, in this case, there is no decision making, because how can one individual by taking decisions make the choice of one. Now, but in general it is not true that these animals cannot take decisions. Now if we think for a moment, so these, suppose we are talking about, now we are talking about the strategies in the realm of the examples what I have giving, that the size of a horn. So this is this decided by the gene. Now uh, so if it is so, then how one can expect such kind of things in animals. So this is answered by the Maynard Smith by introducing the concept of evolutionary game. And the first evolutionary game is the hawk tub game. That hawk tub game. So let me see again. Let me recheck it. Once I want to recheck the payoff. Now, so this is the conventional fighting for perspective of individual selection. So now John Smith says, Maynard Smith says that it is not on the group level. If we think about that, is on the gene level. Now suppose there are two strategies. So let me introduce by this way. Suppose there are two strategies. Hawk and dogs. While hawks escalate fights, so it is the same kind of story that we have seen previously in the case of normal form game. So while hawks escalates fight, dogs retreat when when opponent escalates. So there are these two strategies. Now the cost of injuries if they fight seriously. So the cost of injuries, the cost of injury is, suppose, say C. So if two hawks meet, and suppose the benefit, uh, so benefit by getting a mate is B, Now let me pause for a moment and talk about this benefit here. So this cost and benefits here. So in this evolutionary concept, since we have in the previously we have seen these numbers coming from one's preference was, but in the evolutionary game theory, these since we are talking about the evolution, these uh, these numbers, these benefits and cost is in terms of one's reproductive success. So benefit and cost are in terms of reproductive success. It is called in general, it is treated the rate of reproduction, rate of reproduction as fitness, rate of reproduction, or this equally say the number of offspring, the number of offsprings who successfully reach to their reproductive age. So this is called the reproductive fitness, and when in evolutionary game theory we will talk about the cost and benefit, it is in terms of this reproductive success, fit in terms of fitness. So the cost of injury is C, and the the benefit is, so suppose there is one mate, uh, so the winning of the benefit is B, the winning of the fight, the winning benefit is B. Now you can equally even see when uh, when a male lion fight for getting a pride, then also you will find that sometime the fight escalates to a point where these lions inflict each other a serious injury, but most of the time you will find that they are showing aggressiveness, and they are not escalating fights. One escalate and others become dormant and leave the ground. So why these two types of behavior are there? So why they are not every time they escalating their fight and seriously conflict means inflicting, because the reproduction is a important part. So to for their gene, for the propagation of gene, so why they are not always escalating the fight? So that is the main question. So suppose that winning of the benefit is B. Now if two individuals are fighting, then only one individual can win. So suppose that each individual with probability half can win. So then the for each who are going to fighting with each other, they will get a benefit B minus C by 2. So B is the benefit of winning and C is the cost. Cost is for each other, for everyone cost is C. Now if two hawks meets, so if two hawks meets, so here this is, so let me here in my mind, so only one situation is there, but it there could be also other situation also. So let me rewrite it in this way. Suppose two hawks meet, so let me wait for a moment. when two hawks meet, two hawks meet, the expected payoff for each other, because one can win, then that will be b minus c by 2, and the fight will escalate and one hawks will, and while other is injured, since the both hawks are equally strong, the probability of winning or losing is up. So if a hawk meets a dove, so that is why this, and if a hawks meet a dove, then obviously hawks will enjoy without getting any serious injury, so it will get the benefit b. Now the if uh, and in this case the dove will get, and the dove will get the benefit 0. Now if uh, if if two dove mates, so if two dove mates, if two dove mates, if two doves mates, if two doves mates, then one individual will retreat, and since they will not escalate the fight, there will be no injury at all, but only one among them will win this situation, so in this case it will get a benefit b by 2. Now in this way one can write game, and you can obviously see that this is a strategic interaction. Why? The outcome depends on what is the opponent's strategy. So suppose here let me write the game. So game is hawk and hawk, and this is dove. So if hawk of both of them, so let me write payoff from the player one's perspective. So hawk against hawk, expected payoff is b minus c by 2, and hawk second dove is b, and dove again hawk is 0 because it will retreat, and it is b by 2. So again you can see that this situation can be written as game. Now the question is, we know what are the Nash equilibrium from this hawk dove game, because we can calculate. Now since we are not talking about this in the sense of they are taking a strategy, they are taking strategically decision in sense of Nash equilibrium or in sense of bounded rationality or VNF rationality, we are talking about this is their this is their these strategies are they taken, they have based out from their parents, or the best word would be they are inherited from their parents, and these numbers are basically nothing but the uh, thing but the fitness. So now next question is, then what is the solution of, what is the solution, what is the solution of such strategic interaction? And it is not very obvious what would be the solution, because they cannot take decisions. So what does I mean by the solution? So that is the first question. So what is the meaning of the solution here? Now you will see the solution is a sense as we have talked about the solution in the case of Nash equilibrium and the sampling equilibrium, the solution is a nothing but a state which is in equilibrium or which will not change from its a state which will which is which will not change which will not change. So in case of Nash equilibrium and sampling equilibrium, this not change means, so there will be no incentive to adapt another strategy than the prescribed Nash equilibrium, and similarly the for the sampling equilibrium also. Now what do I mean by not change? So in case of where where my strategy is determined, when my strategy is determined by the bar, so what do you mean by change? So here it's come. So here what does means by state? Here I mean a state by the frequency of the population. How many in the what is the frequency of the population that is adopting dub strategy, and what is the frequency of the population that is adopting fox strategy? So that is kind of a mixed strategies. So mixed strategy is not playing by a individual, but these mixed strategies corresponding to the population. In the population, certain fraction of individuals are taking some action and other fraction of individuals are taking other fraction. Now I am talking about my if my state is the frequency of the population. Now when the population frequency will not change, so that state will be corresponding to the solution concept or equilibrium concept. Now what do I mean by the not change? So here in case of how one strategy, I mean how a new strategy can be introduced to the population. How? So by mutation one can introduce new strategy to the population, and that may change the frequency of the population, or new mutation can overtake the whole population and it will change the population's frequency. So now you see what do I mean by the solution concept. Naturally it is we are we are we are seeking for a state of the population that cannot be invaded by mutation, by any rare mutation, and in this case we are talking about the mutation is very rare. So any rare mutation. So we are seeking for such concept where the populations is the frequent means a state of the population is cannot be invaded by a means it is a invasion proof population. We are searching from does a frequency exist which is invasion proof. Now this concept was introduced by John Maynard Smith, which is called the evolutionary, which is called the state is called, or the strategy means here I am saying the state, and state means evolutionary state. You can say also the evolutionary state, but I will talk about the strategies. So a strategy is called the evolutionary evolutionarily stable strategy. So the solution concept here is the evolutionarily stable strategy. We are asking for the evolutionarily stable strategies. So let us let us see that. So far, now let us now consider the mixed strategy which means here. Suppose the mixed strategies mixed strategies which play hawk with probability probability p and dub with probability 1 minus p. Now for the moment, let me for the moment, since I have talking about the strategy or state means the frequency, that is true, but here the evolutionary stable strategy means suppose there is a population and every individual in that population, every individual in the populations are taking a mixed strategies. So mixed strategy is inherited by birth. And what is the mixed strategy? So with probability p it will escalate the fight, and with probability 1 minus p, with probability 1 minus p, it will remain dormant or it will retreat in a fight when uh, other escalate. So this means dub strategy, and this probabilities p1 minus p is determined by birth, and only one can change its probability by mutation. Now suppose there is a infinite population of individuals, and every individual, this population is called the monomorphic populations, monomorphic and homogeneous population, and it is also well mixed population. So suppose that every individuals are taking this kind of strategies. So now suppose a slight mutation came into the population, slight mutation came into the population, very small fraction of mutation came into the population. Suppose epsilon fraction of mutation came into the population whose frequency is, suppose, let me let me let me introduce p. Suppose that in this way, then it will be very useful for writing. Suppose that a mixed strategy is p star and 1 minus p star is evolutionary stable strategy, so ess. So and now a small fraction of mutation who uses small fraction, suppose epsilon mutation, come into the population who uses the strategy p. So the strategies again. So similarly this strategy with probability p it will play hawk, and 1 minus p it will play dove. So 1 minus p. Now what will be when this the strategy p star will corresponding to the ess? So let us think about this situation. So the first, it has to be, so on average, so let me sit then above. So if the fitness, the average fitness of, so if I go back to here, I will not go back. So what is the average fitness? Average will find that average average fitness of uh, this p star. So average p star, so one strategy is denoted by p star. What will be the average fitness? So average fitness will be the fitness it get when a p star is playing with p star. With which probability it will play with p star? 1 minus epsilon, because 1 minus epsilon fraction of the population is choosing a strategy p star, and with probability epsilon there is. So this is the expected fitness when p star is playing p star. So I will calculate one such things, then you will get idea. So let me write first. So 1 p star p. So the average fitness, as Darwinian selection says, so average fitness of this p star has to be greater than the average fitness of the average fitness of the mutation. So with 1 minus epsilon probability, a mutant will interact with this natal population, means the the natal population individuals who are there, and with epsilon probability it will. Now if you when epsilon is very near to 0, epsilon is very small, then since the mutation is very near rare, so since mutation is very rare, so that's why when it will be true, it will be true when if epsilon is 0, if either e p star p star is greater than e comma p star. If it is true, then it will be always, this condition will be always true. Or either if these become equal, p, sorry, not p star, if it becomes equal, then we have to check these conditions. So this e p star has, again playing against p, has to be greater than p playing in p. So this is p, I think. Now if these two condition, one of these two conditions satisfied, then we will call is the p star is ESS. Now one thing remains, what is the meaning of e p p star? So let us calculate 1 p p star. So this means when, so let me copy and paste this payoff here. Okay. Hmm. Okay. Now what does means p star? So p, when a player with strategy p, so a strategy p star, let me write p star, or in general strategy p1, that means p1 means with probability p1 it will play this, and with probability 1 minus p1 playing dove is against p2 means p2 1 minus p2. Then what do I mean? What is the expected pay of player 1 get? What is the expected pay of player 1 gets when it is playing against p2? I am saying that with probability p1, with probability p1, since these two players are independent, so with probability p1 it will get b minus c by 2 into, so it is playing with probability p1 hawk, and if it's play hawk, what is the probability that it will get b minus c by 2? It is obviously p2. And what is the probability it will get b? That is p into 1 minus p2. Similarly 1 minus p1 into 0 into p2, it will get 0 with probability p2, and it will get p by 2 with probability 1 minus p2. So this is the expected payoff when a p1 strategy player interact with p2, and this p1 strategy will get this. And similarly one can calculate the p2 case. So this expected utility is nothing but this expected utility, and expected here not expected utility, it is called the expected reproduction rate, or expected number of offspring it will get, or expected number of offsprings will expected number of offsprings one so one animals who is adapting whose strategy is p1 and 1 minus p1 will get when it will interact with individuals whose strategy is p2 1 minus p2. And the concept of ESS is such that it is generally the concept of such that no mutation can overtake the population, so that means the strategy of the population remain fixed. So that is the equilibrium concept, and you will find that if when it will happen, so if I use the Darwinian concept, so if the average fitness of this p star is higher than the average fitness of this mutant, then this p star cannot be invaded, this population of p star cannot be invaded by this mutant p. And when it will happen, we have calculated that it will only happen when this either one of these two conditions satisfied, and these conditions are called the ESS, evolutionary stable state. Now if we find the evolutionary stable state corresponding to this, you will find that, so this is the pure, obviously whatever we have talked about, it is called the concept, it is seeing the evolutionary stable state strategies from the perspective of population view, and it is called the mixed evolutionary stable strategy. Now similarly one can also write that what will be the um, what will be the mixed strategy. Once one can also find that what will be the pure strategy. Pure strategy is, instead of this p1 1 minus p2, one can find that with p equal to 1 and with p1 equal to 1 and p1 equal to 0, so one can find that pure strategy. So pure strategies is nothing but the corresponding hawk is a pure strategy, and when what it is corresponding to p1 equal to 1, and dove is a pure strategy, it is corresponding to p1 equal to 0. So that's it. Now let us check that what is the ESS in this case, in this example. So first let me calculate this p1 comma p2. You will, so let me calculate that. So if I calculate it, so this will be p1 into b minus c by 2 p2, okay, plus p1 minus p2, okay, and here it is p by 2 1 minus p1 1 minus p2. So now let me generalize this thing. So b minus c by 2 p1 p2 plus p1 minus b p1 p2 plus b by 2 1 minus p1 minus 2 plus p1 p2. We take every p1 p2, so this is p by 2 p by minus c p1. If we take common of p1 p2, then you will find that b minus c by 2 minus b. I am taking these terms, these and plus this term b by 2 p1 p2, then left term is this term plus p1, this is plus p by 2, this is minus b by 2 p1. So if I combine these two terms, I'll get b by 2 p1, and only left term is these two common, b by 2, and this is minus p by 2 p2. So this is only this p by 2, this b by 2 is p, so these b cancel, so it is like that p by 2 plus b by 2 p1 b by 2 plus p1 minus b by 2 p2 plus minus c by 2 p1 p2. Now if I take b by 2 common here, b by 2, so it will 1 plus p1 minus p2 minus c by b p1 p2. Now what is the Nash equilibrium here? So what is the mixed ESS here? I will say that it is the Nash equilibrium here is b by c. Nash equilibrium is b by c. Sorry, it is not Nash equilibrium. It is, here we are trying to find the evolutionary stable strategy. So p star is equal to b by c is mixed ESS, or say it is a ESS. Now to check that, let us first find what is the this expected utility E p star E p star. So this quantities, so E p star where p1 p2 same, which is p by 2, which is p1 p2 is same. So if I put there, so the p star cancel, so it will p by 2 into 1 minus c by b into b by c into b by c b by c into b by c. So this this is cancelled, so it will become b by 2 1 minus p by c. What is the p star? And you will find that p star is p star. If you put it here, b by 2 plus p minus p star, that means b by c, minus c by b into b by c. Here I think if you write it, p star is 1. What is p star? 1 p. So here the when p is playing against p star, it will get 1 plus p1 minus p2. So this it will get into b by c. So this is cancelled, so this will become b by 2. Okay, I missed a point here. So this is c by b into p star means b by c into p. So this is cancelled. So this p cancelled, and one remains 1 minus p by c. And we have to calculate what p star is getting, since these two quantity equal. As if I go back to the Nash equilibrium conditions for ESS, you see that first condition is not true. However, this condition is true. E p star equal to E p star, E p star, that is b by 2 1 minus b by c. Now we have to check what a p star is getting by playing with p. So that will be b by 2 1 plus p star. P star means b by c, b by c minus p minus c by p into b by c into p. So that will 1 plus b by c. So this will be minus 2p. And what is the case last? We have to find what a p star, what a p is getting while playing with a p. So that will be b by 2. Again that pp is cancelled, so 1 minus c by b p square. Now since these two are equal, now we have to check that whether E p star p is greater than E p comma p. So to check that, what we will do, so that means if E p star p is greater than E p p, then E p star p minus E p comma p has to be greater than 0. So we'll check that. So first E p star p, since b is a positive number, so b by 2, by take b by 2 common, so one get 1 plus b by c, 1 plus b by c minus 2p minus 2p minus EPP, so minus 1 and plus C by B P square greater than 0. So this is B by 2 is positive number, so we have to check whether this number is a positive number or not. So 1 cancel, so P, if I take P by C common, so you will get or maybe not take common, so you will get here. So that means we have to prove that B by C, suppose root P by C square minus 2 into root P by C into root C by P into P, so this is cancelled, plus root C by B into P square has to be greater than 0, and naturally it is greater than 0. Why? Because it is a minus C by B into P. It is a uh, it is a number which represent can be represent as a square of this quantity, and square of anything we know unless it is not a imaginary number, which is not in this case. This is not an imaginary number because this is a this represent the fitness of this individual, so this is a real number. So we know that the square of a real number is always positive, so this quantity is positive. Since this quantity is positive, we know that E P star minus P minus E P P is greater than 0, so that means E P star is E P star P is greater than E P P, so that means P star equal to P by C is a yes. Now you see that no other mutant who is using other than B by C can invade the population. That means any other the population can resist the any mutant who is using the strategy other than B by C. So this is the concept of evolutionary stable strategies. Now these concept can be, means every concept can be represented in terms of dynamics, and I only hint about, because it is not, this course is not about the dynamics, but let me hint about the dynamics which is associated with this Darwin evolution, which is called the replicator dynamics. Replicator dynamics, and through this replicator dynamics which captures the Darwinian evolution, which is nothing but the frequency, the change of frequency will be proportional to its current frequency, it's obviously current frequency, and the fitness of a suppose hawk minus the average fitness. So let's not talk about this Darwinian replicator dynamics. I only want to mention about the thing that through the Darwinian evolution, to capture the Darwinian evolution, one can write a dynamical equation which is known as the replicator equation, and using those replicator equation one can capture the evolution, and one can capture the evolutionary stable strategy. So that's it for the today's class, and this is the end of this lecture series of the solution concept. We have learned the solution concept of classical game theory, which is Nash equilibrium, the solution concept of game in the behavioral game theory, that is sampling equilibrium, and the solution concept corresponding to evolutionary game theory, which is ESS or evolutionary stable strategy. So that's it, and thank you for take part in this course.